Today we're going to talk about linear programming. And it's big words, but what it comes down to oftentimes is, can you graph? Because if you can graph, then it's definitely a big part of linear programming. As you see, graphing a set of inequalities on the same coordinate plane to find a maximum or a minimum function in two variables is called linear programming. So graphing is a big part of linear programming. The intersection of a system of inequalities represents all combinations of ordered pairs that satisfy each of the inequalities. And the inequalities have a special name. They're called constraints. And when we're graphing inequalities, remember that implied in an inequality is that it needs to be shaded, and it never says shade. But the intersection of the graph is called the feasible region. When a system of inequalities produces a convex polygonal region as a solution, so convex polygonal region, well, a polygon could be a quadrilateral like a square. It could be a triangle. It could be a pentagon. That's a convex polygonal region. The maximum or minimum value of a related function will occur at a vertex of the region. And if we do have a polygonal region, when the graph of the system of constraints is a polygonal region, the region is said to be bounded. Oh, is that last letter? And finally, the notation f parentheses x comma y is used to represent a function with two variables, and it's read f of x and y. And I went pretty quickly through the words, I know, but what I find is that there is some vocabulary that goes with these problems, but I think that the examples are probably more helpful for you than the words themselves. And I'll throw the words in so that we can kind of get an idea of what they are. So our first one says, use the following system of inequalities to complete the questions below. Again, what I want to remind you of is that we've got greater than or equal to or less than or equal to in these problems, and that means that we are going to have to shade, and the directions never say shade. So we look at this first one. It says y is greater than or equal to negative x plus 2. What's the y-intercept of our first inequality? 2. What's our slope? Negative 1. If you prefer, you could have rewritten this as y is greater than negative 1x plus 2. And remember that slope is defined as rise over run, so it's negative 1 over 1. And we're going to start with b equals 2. And then we're going to go down 1 to the right 1, down 1 to the right 1. And we can also go up 1 to the left 1, up 1 to the left 1, up 1 to the left 1. And you have a ruler, even though I know that I'm going to draw freehand. There's our first inequality, which is also a constraint. We're going to be graphing 3 of them. The next one we're graphing is y is less than or equal to 1/4 x plus 2. And you may be ahead of me, but we need to identify what's the y-intercept. Well, it's 2 again. And our slope this time is 1/4. Again, slope is rise over run. So we're going to start at b equals 2. We're going to rise 1 and we're going to run for the right. Rise 1 for the right. Or we can go down 1 and 4 to the left. Here's our second constraint. Thirdly, y is greater than or equal to 3/2 x minus 3. Our y-intercept is -3 this time. Our slope is 3/2. B equals -3. So it's going to be up 3 to the right 2, up 3 to the right 2, up 3 to the right 2. We can also go down 3 to the left 2. And here's our third constraint. So this red line and the green line and the blue line, they are solid lines because there's an equal to in each of those inequalities. They are also called constraints, as I've said before. And what we need to do is we need to shade. And what we're looking for here, without spending the time on shading in this particular problem, I will on the next one, is we're looking for a convex polygonal region. Well, what you may see, and at least I hope what you might see, is that there's a triangle in here that is a convex polygonal region. And that part where I just shaded and is yellow, that yellow part is called the feasible region. What we're looking for when we do these problems is we want to come up with the vertices of the polygon, in this case a triangle, and the vertices are going to be here and here and here. I'm a little bit off on that third one, but I know what the points are. And that's what part B says. So we've done part A, we've graphed the system. By the way, we're going to use f of x comma y equals x plus 3y in a couple minutes. But the 3 vertices, and they don't have to be in the same order that I write them, but you have to have all 3. The first one is 0, 2. The second one is 2, 0. And the third one, and I hope your picture is a little bit better than mine, is 4, 3. And once we've identified those, what we're going to do is we're going to use our f of x and y function, which is f of x comma y equals x plus 3y. We're going to use that to help us figure out what's the maximum value and what's the minimum value, and those values occur at one of the vertices of our triangle in this case. Remember that the order pair 0, 2, that's xy. And all of them are xy. So we're going to start with f of 0, 2. 0 is going to go back into our function for x. And 2 is going to go back in for a function for y. And 3 times 2 is 6, so 0 plus 6 is 6. The second order pair that I have listed is 2, 0. So 2 is going to be our x value, and 0 is going to be our y value, and we're putting it back into the f of x and y function. So this one's going to be 2 plus 3 times 0. Well, 3 times 0 is 0, so 2 plus 0 is 2. And we have one more order pair, 4, 3. So it's going to be f of 4, 3. 4 is going to go back into our equation for x, and 3 is going to go back in our equation for y. 3 times 3 is 9, so 4 plus 9 is 13. Now that we've used our vertices to find those values, we want to identify what's our maximum and our minimum value. Well, maximum means the biggest value. So our maximum is the biggest value between 6 and 2 and 13, which is 13. And we get that from the point 4, 3. We put 4 back in for x, we put 3 back in for y. The minimum value is the smallest value between 6 and 2 and 13. And our minimum then is going to be 2. And that happens at the order pair 2, 0. There's an example of the basics of linear programming, which we're going to practice today. Continue practicing. It comes down to things like graphing. Can you graph? And on our next example here, the question is, how do we graph something like y is greater than or equal to 2? Well, in other words, what we're graphing, do you know? In other words, what we're going to be graphing is y equals 2. And what axis do we cross when we're graphing y equals 2? Well, we're going to cut through the y-axis at 2. In other words, y is greater than or equal to 2 is a horizontal line. And once we can identify that fact, the second inequality listed on our problem here says 1 is less than or equal to x, which is less than or equal to 5. Or another way of stating it is x is between 1 and 5. And what we're going to graph is we're going to graph this line x equals 1. And we're also going to graph x equals 5. And both of these, because they're x equals, are vertical. I do recognize that they're less than or equal to. But in terms of graphing, what we want to get is we want to get this on paper. Again, hopefully your pictures are better than mine. So that leaves us with our third inequality. And for our third inequality, we need to go back and put that into slope-intercept form. Just a reminder that slope-intercept form is y equals mx plus b. In other words, we're going to be solving this inequality for y. And the inequality that I'm speaking about is y minus 3 is less than or equal to x. So we don't have to do too much work. but we're going to add 3 to both sides. And we get y is less than or equal to x plus 3. And on this particular inequality, we need to be able to identify what does b equal, and hopefully you're saying 3. And what does our slope equal? Well, just a reminder, there's an unwritten 1 there. We can write it in there. And slope is rise over run. It's 1 over 1. And we're going to graph that. Because all of our inequalities have equals in them, we can use a solid line. B equals 3. And then it's going to be up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. And we can go down 1 to the left, down 1 to the left, but on this particular problem, once we get it graphed, it's harder to identify the convex polygonal region. The green lines, the red line, the blue lines are constraints. And what we need to do is we need to figure out where to shade. And you might want to wait to shade until I shade, so that your picture doesn't get completely jumbled up and you don't know what's what. But when I start here, I'm going to start with the 2 green lines. Because once again, the way to read that inequality is that x is in between 1 and 5. So when I shade this, I'm going to shade just a little bit. Enough to know that I'm going to be in between these 2 lines. Again, positive 1 is less than or equal to x is less than or equal to 5. X is in between those 2 green values. Going to go back to the first inequality, which is y is greater than or equal to 2. Where is y greater than or equal to 2? Above or below that blue line? It's going to be above. Now our fallback here is that we could go ahead and we could pick 0, 0, and we could put that back in there, and does it work or does it not work? But usually with horizontal and vertical lines, we do a little bit better. But I am going to do the 0, 0 for our red line. And I'm going to put it back into the original inequality, which says 0 minus 3. And the question is that less than or equal to 0? And by the way, here's 0, 0. So if we simplify that a little bit, 0 minus 3 is negative 3. Less than or equal to 0? Yes. So we're going to shade where it is, and I'm not going to shade a lot, because we want to be able to identify where is that polygon. And that polygon, before I shade it for real, is this trapezoid here. Now is maybe the time that you want to darken that. And I will shade it. Because once we can identify that, then we can come up with the vertices, and we can identify then the maximum and the minimum values. So as I go back and look at that picture, let's even mark it up a little bit more with our vertices. There's a vertice here. There's a vertice here. there's a vertice, I think it is up a little bit higher than what I've got on my picture in there. Once again, you need to have all 4 vertices. They don't have to be in the same order that I list them. You just have to have all 4 of them. And you might have to help me with one of them, but what I can see is I have 1, 2. I think I have 1, 4. 5, 2. And then I think I'm going to go 5, 7. Is that what you have on your paper, those of you using a ruler? 5, 8. Thank you. And again, that's just the downfall of not using a straight edge. But once we identify those values, now we're going to use that bottom equation, which says f of xy equals 3x minus 2y. And we're going to take those 4 ordered pairs and we're going to put them back in. The first value is going to go back in for the x. The second value in the ordered pair is going to go back in for the y. So it's f of 1, 2. So 1's going to go back in for the x, 2's going to go back in for the y. So it's 3 times 1 minus 2 times 2. Well, 3 minus 4 is negative 1. Then we take the next order pair. Again, you don't have to have the same order, but you're going to have to still do the same math. 1, 4. F of 1, 4. We're going to put 1 back into the equation for x, and we're going to put 4 back into the equation for y. So we get 3 times 1 minus 2 times 4. Well, 3 times 1 is 3, and 2 times 4 is 8. 3 minus 8 is negative 5. You might have to go under your graph like I'm going to do to get the other 2. We're still working with f of xy equals 3x minus 2y. This time let's put in the value of 5, 2. So f of 5, 2 is 3 times 5 minus 2 times 2. 3 times 5 is 15, 2 times 2 is 4, 15 minus 4 is 11. And our last value is 5, 8. The 5 is going to go back into our function for x. The 8 is going to go back in there for the y. So it's 3 times 5 minus 2 times 8, which is 15 minus 16, which is negative 1. And once we get those values there, we can go back and we can identify what's the maximum and what's the minimum value. Maximum is going to be the biggest value, and it's going to be the biggest value between negative 1, negative 5, 11, and negative 1. Well, our maximum is 11. And then we want to write down what ordered pair did we use to get that value. And the ordered pair that we use is 5, 2. The minimum is the smallest value between negative 1, negative 5, 11, and negative 1. Remember that negative 5 is smaller than negative 1 because it's farther to the left on the number line. So negative 5, we got that value from the ordered pair 1, 4. By the way, if it happened that negative 1 was the smallest value, we would have 2 minimum values in this problem. It didn't work out that way, but you could have 2 minimums or 2 maximums for that matter. But as we take a look here at our last example, it says use the following system of inequalities to complete the questions below. It's the same process here. We're going to graph, we're going to shade, we're going to come up with the feasible region, going to come up with the vertices, and then the maximum and the minimum. The thing that I think we teachers worry about most is can you identify what kind of line is a horizontal line and what kind of line is a vertical line when graphing? Because in general, I think what we've seen is that you're really good with slope-intercept forms. So as we look at this one, and I may only get this one graphed at this point, but y is greater than or equal to 2. Is that horizontal or is that vertical? And hopefully you're thinking that this is a horizontal. Luckily, all of our lines today, our constraints, have had greater than or equal to or less than or equal to, which means solid lines. There's our y equals to, and we'll shade it in a couple minutes. Remember, when it's y equals, we're crossing the y-axis. When it's x equals, we're crossing the x-axis, which is why this second value here is a vertical line at -2. So our third constraint, x plus 2y is less than or equal to 12. We need to put this into slope-intercept form. We need to solve for y. So we're going to subtract x from both sides. We get 2y is less than or equal to negative x plus 12. Divide by 2. And we end up with y is less than or equal to negative x over 2 plus 6. What's that number in front of the x? 1. And we need that for our slope. Our y-intercept is 6. Our slope is negative 1/2. And here's the 6. And it's down 1 to the right 2, down 1 to the right 2, down 1 to the right 2, down 1 to the right 2. We can go up 1 to the left 2, up 1 to the left 2. And the nice part about this one here is that I think we can see our convex polygonal region. We only have one. We could go back and use our shading techniques. But ultimately what we're going to end up with here is that triangle. And our coordinates are here and here, and I think it should be really here. Again, you don't have to have the same order as me, but you need to have all three of them. Our -2, 2. And can you help me out? -2, 7. And I think 8, 2. And we're going to take those values and we're going to put them back into the function of x, f of xy equals 2x minus 3y. So we have f of -2, 2, which equals 2 times -2 minus 3 times 2, which is -4 minus 6, which is -10. We have f of -2, 7, which is 2 times -2 minus 3 times 7. 2 times -2 is -4, minus 21 is -25. And f of 8, 2 is going to be 2 times 8 minus 3 times 2. 16 minus 6, which is 10. And as we're running out of time here, just to finish, we can label these. Our maximum value is the biggest of these three, which is here at the 10 from our order pair 8-2. And our minimum value is the smallest value between negative 10 and negative 25 and 10. And negative 25 is our minimum value at negative 2, 7.